Okay, I wanted to talk about this a little bit. And we have two different frequencies going on. Right here, or I should go over here and go over here. 20 and 10, and different phase angles and the like. Here's the trick. This is a voltage source. You use superposition. You gotta use superposition. You treat this voltage source as a short and solve everything using this voltage source. Then you reverse it. You have two circuits. You treat the second voltage source, or excuse me, the second voltage source is a short, and you solve that circuit. Then you treat the first voltage source as a short, and you solve for the second one. This is this, and you take the sum. You sum the two. So you're going to have the current is going to be a sum of two different frequencies. There we go. And you superimpose the two solutions right there. Okay, where is it? This is solution 1 at 10 radians per second. There we go. Solution 1. Solution 2 at 20 radians per second. This is how transistor radios work. Things come in at different frequencies, and they amplify, and you get current out, and eventually, once you get through all the circuit, you get sound, music, etc. MATLAB, like I said, I use ECE202 because it's free compared to MATLAB. Outputs look identical. So you can use MATLAB as you can use MATLAB or ECE202. Let's see, and the author doesn't know about here's the pi over 180, like I do quite a bit. I use cosine D, by the way. So if I have angles in degrees, cosine D finds the cosine of the angle in degrees. Sine D, same thing. Sine of the angle in degrees. You'll notice I also use ABS and ARG. So instead of finding the magnitude M, I'll use those two things to find the angle and the magnitude. Going the other direction, let's see, if I have an angle and a magnitude, instead of cosines and sines and stuff, I will just write M times exponential of I do need radians when I use the exponential form. ARJ. You guys may have noticed me doing that as I solved some of the problems previously. And that should give us the same answer. Let's just double check that. 10 and 45. There we go. Z equals 10 times exponential of 45 degrees times pi divided by 180. 45 times pi times j divided by 180. So inside this converts, pi over 180 converts degrees to radians. Or sometimes I know 45 is pi over 4, so I'll just write pi over 4. And voila, same thing. Right there. Right there. MATLAB and New Octave handle complex numbers pretty well. And then going in the different direction, they do other things. If you have an angle and so forth. At least they know. At least the author knows about ABS. Maybe didn't know about argument or ARR. Okay. Let me go back. I use ARG. I wonder if, okay. I wonder if that's a typo right here. If they really meant to say, oh, ARR equals angle of Z. Well, let's try angle. I'm sorry, angle is the function. Would that work? It doesn't like it. And no wonder I didn't put in the right thing. There, angle of Z in radians, 0.78. Okay, yeah, it does it. Angle does it. Arg does it too. Okay, so that's something new. Something I'm not used to. You can use this function to find the angle in radians, and then you got to convert it to degrees, like I've been doing. Okay. Now, noise rejection. This is the multiple frequencies are good for analyzing noise. If you have noise at a separate frequency, you can use some sort of circuit to get rid of it. J omega L, for example, or yeah, that noise frequency, especially if it's larger than this voltage, then this will block it. This is a good blocker. Let's see, do we have the, there we go, higher frequencies than the signal, and we want to reduce it by a factor of 10. So we have the, we want to make sure that this is 9 times bigger than this. The impedance J omega L has to be 90 kilo ohms. Oh, I'm sorry, you got to use complex numbers. In DC, that would be true. In AC, not quite so much. A voltage divider, but a voltage divider that looks like this. So we want this to be 1/10 at this frequency. Okay, this is kind of a cool little circuit. This is an active circuit using op amps and only capacitors. Or is it only resistors, I was thinking. What it can do is it converts by the proper choice of Z1, of the impedances, you can get any desired equivalent impedance. So the final formula worked out to be this when you went through all the analysis. And for example, you could take, if you take Z4, for example, to be a capacitor, it acts like an inductor. And Z1, Z3, Z2, Z1, Z2, and Z5, and Z3 can be resistors. And then you have one component that's a capacitor. And it makes the equivalent look like an inductor. That's kind of cool. Yeah, makes the equivalent look like an inductor. So inductors are big, lots of copper wire, magnets, and all that stuff. This way, you can use, say, less expensive components to get to the inductance you want. Okay. Gains larger than 1, and I guess I wasn't quite done with everything I wanted to talk about. So we have one more video, we have a little bit more. You can't get power gain larger than 1, by the way, but you can get voltages that are large. The voltage out is a lot bigger than the voltage in. But not power, not energy and power. So next time I'll pick this up.